Okay, I guess we'll get this started. Welcome everyone, both here and online. There's maybe almost the same number, maybe more online. So welcome everyone. This is the oral examination for Austin Williams. He's in the Marine Resource Management Program in CEOS, and oral examination for his master's defense. Committee is here. We will listen to this presentation, and the rest of you can as well. He'll present for about a half an hour, 45 minutes, something like that. And then you'll have time to ask questions here in public defense, both online and here. And then the committee will go to another place and finish the examination for Austin. So welcome everyone. And I'll now introduce Austin Williams. He's from San Diego. He grew up in San Diego, I guess. Grew up. Yeah. I should have known that, but I didn't realize it again until this morning, because it's sort of a little bit of full circle. He's just recently accepted a job back in San Diego with the Army Corps of Engineers, in part due to maybe his training here. As a regulatory project manager. Austin got his undergraduate degree in marine biology at the University of Manoa in Hawaii in 2011. And then he came to Newport shortly thereafter. And he's worked in a number of positions here in Newport. First as a fisheries observer with the Pacific States Marine Fisheries Commission, and then did some volunteer scuba work with the Oregon Department of Fish and Wildlife for the Marine Reserves Program. And then he's a port and stayed with Department of Fish and Wildlife, or had some other jobs there as a port sampler, and also part of the acoustic mapping, assistant acoustic mapping program. And then he also worked in Chris Langdon's mollusk and broodstock program over here, working on dulse and aquaculture as well. He came to the MRM program in 2020. 2020, as you all know, was a year that COVID sort of came in. So he's a COVID graduate, which changed his program a little bit. It actually rushed it a bit. He would have probably done some field work with us in 2020, summer of 2020, but had to do it all in 2021. And so that made a little bit of a difference. You know, the usual struggles, he can tell you about those, I guess. And he had, but despite those setbacks, he persisted, and now we're finally here. He was funded on a Sea Grant, Oregon Sea Grant program that we sort of wrote a portion of on aquaculture and ecosystem-based management and aquaculture. So a small part of that, did his field work in Tillamook Bay, and he's going to tell you all about that. I think that's most everything. I would say he's also an artist. So the first presentation that I saw for the State of the Coast conference, he did art at that, which that was interesting for me, also as an advisor. So that was cool. That's one little highlight. So today he's going to talk to you about, I have his long title right here, I guess. Diel and tidal patterns of nekton communities in eelgrass and shellfish aquaculture habitat in a Pacific Northwest estuary. So Austin.
Well, thanks for that introduction, Brett. Well, as you know, I'm Austin Williams, master's student at Oregon State University in the Marine Resource Management Program. And I'll be discussing diel and tidal patterns of nekton communities in eelgrass and shellfish aquaculture habitat in a Pacific Northwest estuary. This work was funded by Oregon Sea Grant as part of the West Coast Aquaculture Collaborative in an effort to expand opportunity for sustainable shellfish development in the Pacific Northwest. I'm going to start out by giving you a little bit of background into aquaculture in the Pacific Northwest, discuss my research objectives and methodology, and then report the conclusions I made and some broader impacts of the study. The picture to the right was taken during field season last year and shows our team getting ready to conduct some fish surveys out in Tillamook Bay. You'll notice we're wearing masks due to the onset of the COVID pandemic, which was pretty challenging to work in the water with a paper mask for 8 hours. So the Food and Agriculture Organization of the United Nations projects global seafood consumption to increase over the next decade, with production unable to meet demand by 2030. And shellfish aquaculture is a growing industry that continues to fill this increased demand as consumers seek out healthy and sustainable seafood options. In the Pacific Northwest, shellfish aquaculture is valued at $270 million a year in 2021 and provides 3,200 coastal jobs. In Oregon, aquaculture is valued at about $10 million a year and is largely focused on the Pacific oyster, Cassistraea gigas, with 70% of the aquaculture occurring in Coos Bay, and with Tillamook Bay being another important aquaculture hub for Oregon. The picture to the right is one of our sample sites in Tillamook Bay, showing some on-bottom aquaculture in a muddy habitat. It sounds like somebody might have their microphone on. So the estuarine landscape is dynamic and stratified. It's composed of a mosaic of habitats that are influenced by tidal cycles and terrestrial watersheds. Rivers carry dissolved nutrients and particulate organic matter through salt marshes across tidal flats, over eelgrass meadows and oyster beds to the bay, where they're then mixed with nutrient-rich upwelled waters that create the perfect conditions for plankton blooms, and which there in turn support prey recruitment and drive complex interactions between organisms and landscape. Estuaries provide many ecosystem services. They act as nursery grounds for many species of fish and invertebrates, support shellfish aquaculture and commercial fishing industries. They protect coastlines from erosion, facilitate blue carbon burial, and offer a wide range of recreational opportunities such as kayaking and fishing. Grab my laser pointer. So these photos here are of some of the research sites that we've kind of worked out over the last couple of years. We spent some time up in Willapa Bay in Washington and got to see some nice eagles out on the estuary and the mudflats. We've seen lots of eelgrass meadows, off-bottom aquaculture up there in Tillamook Bay. And you'll see there's a wide variety of habitats within the estuary, from muddy sandy bottom to the rocky intertidal. Photo to the right is me snorkeling for crab in Yachats Bay, which has some very interesting underwater features with a lot of rocky habitat up there as well. So shellfish aquaculture is inherently tied to the estuarine ecosystem. It often modifies the landscape with biogenic and artificial structure, and the structure provided by aquaculture is increasingly being recognized as functional habitat. That helps to further drive the substantial biological, economic, and cultural value of our estuaries. And photos here depict some more off-bottom aquaculture in Tillamook Bay on these long line structures here. And there's several producers in Tillamook Bay. We have Pacific Seafoods, whose building that is up there. And then to the right is the Oregon Oyster Company in Yaquina Bay. And down below, we see pictures of Netarts Bay and Yaquina Bay. So there's a big diversity of landscape and businesses, and they're all interacting together. So eelgrass meadows play an important role in estuarine ecology, and they're federally protected as essential fish habitat and are a habitat of particular concern under the Magnuson-Stevens Fisheries and Conservation and Management Act. Importantly, they're considered to be ecosystem engineers. They provide structured habitat, alter water chemistry through photosynthesis and respiration, filter suspended sediments. They can sequester and store carbon, and they offer possible solutions to climate change when they do that. Eelgrasses are experiencing global declines. However, they're regionally expanding in the Pacific Northwest. This may be due to the introduction of the invasive eelgrass, Xerostra japonica, which typically grows higher on the tidal flats than the native eelgrass, Xerostra marina. Habitat offered by eelgrass is seasonally variable, with generally greater coverage and biomass in summer compared to winter months. The video that you've been watching was one of our sample sites in some sparse eelgrass habitat in Tillamook Bay. And we were really fortunate during a lot of our surveys to have some very nice visibility. So estuaries are home to many commercially and economically important species. These photos to the right were collected during our survey effort and show a staghorn sculpin, the top left, English sole, Chinook salmon, shiner perch, and Dungeness crab. All these species are important both ecologically and pretty much all commercially, except for the staghorn sculpin and shiner perch, which don't really have commercial fisheries. But how Necton use estuaries and habitats have been heavily studied in recent decades, with most reporting that use varies both spatially and temporally, making it difficult to generalize findings across different regions and estuaries. However, a number of studies have found that many species that occupy the intertidal zone are habitat generalists, with few species exhibiting specific habitat associations. And the main driver of habitat use appears to be seasonality, and it's further influenced by local geomorphology and diel period, and in some cases, tidal cycles. Continuing the sustainable development of shellfish aquaculture and use of marine resources requires us to adapt to an ever-changing environment. Climate change, ocean warming, ocean acidification are some of the most pressing issues that growers must face. Terrestrial and marine heat waves are becoming more common. The July 2021 heat wave brought coastal temperatures up into the 90s, resulting in catastrophic loss of oyster beds, while increased frequency of marine heat waves threatened shellfish closures due to toxic algal blooms, higher bacteria counts, as well as crop loss due to hypoxic events. The graph on the left describes the increase in CO2 over the last couple of decades, which is a red line here. And as carbon is introduced into the atmosphere, it's absorbed into the ocean, increasing the partial pressure of CO2, which kind of in turn works to decrease ocean pH, which increases acidity. So since the pre-industrial era, the ocean had a pH of about 8.3, and right now, average ocean pH is about 8.1, which is 30% more acidic. And so waters that upwell along the Oregon coast are reflecting atmospheric conditions of 30 to 50 years ago. And this causes localized ocean acidification that has caused large-scale hatchery die-offs at some oyster farms, which now must buffer water against high pH or low pH as low as 7.6 using dosing systems in their hatcheries. And so this map here shows the pH of coastal waters off Oregon as of yesterday. And you can see the lighter green colors are areas where we have some upwelling, and the pH there is about 7.6, where it's closer to the low 8s out in the ocean. So these coastal areas where we're farming oysters are more susceptible to ocean acidification, which can basically slow down growth and cause larval mortality. Conflicts between the oyster aquaculture industry and various stakeholders, such as environmental groups and sometimes state regulatory agencies, are increasing due to perceived environmental threats. Some stakeholders are concerned about habitat loss, negative ecosystem level reactions, invasive species, reduction of water quality, changes to the viewshed, economic impact to other industries such as tourism and fisheries, as well as increased marine debris and land use conflicts such as beach access. And there's also a general sense of NIMBYism, or not in my backyard. A lot of people just don't want to look out and see aquaculture in what they view as a pristine environment. So some of the biggest barriers to entry in aquaculture development are regulatory in nature. There's a lack of leasing space, with agencies having limited resources available to evaluate tidelands for their aquaculture potential and accommodate environmental concerns. Shellfish aquaculture operations often overlap with eelgrass meadows, which, as I mentioned, are federally protected and are managed differently between states. California and Washington, for example, have a no net loss policy that requires remediation of any negative impacts to eelgrass beds by aquaculture activity. Oregon has some state regulatory measures in place, but none are specific to eelgrass, rather just a broad coverage of underwater vegetation. So with the inevitable expansion of the industry and increased public scrutiny, growers need to strictly conform to current regulations, while they also need to advocate for sustainable expansion of their industry. One of the biggest problems growers face are burrowing mud shrimp, Neotrapea californiensis. And we have some other people in the lab working on this. But if you take a close look at this picture, you can see a lot of small holes in the mud. And these holes were made by mud shrimp, also known as ghost shrimp. So mud shrimp are native to the Pacific Northwest and burrow in the sediment over a short period of time. They can smother oyster beds. Farmers and some researchers in this room have spent years trying to find cost-effective methods for controlling ghost shrimp. The most successful method of treatment was a neurotoxin pesticide called carbile, which caused the shrimp to smother in their burrows. But this was discontinued in the early 2000s over public outcry using pesticides in the estuary, and regulations were put into place prohibiting its use. Farmers are still trying to find ways of controlling mud shrimp, experimenting with adding gravel to settlements, pressure washing burrows, electrolysis, and natural chemical agents such as capsaicin from habanero peppers, but nothing has worked or has shown to be cost effective in controlling them. So sustainable expansion can be accomplished through ecosystem-based management, which is an emerging strategy for the management of coupled social ecological systems. Importantly, EBM considers the human connections in the ecosystem to be part of the ecosystem. It focuses on place and uses spatial and temporal scales. It considers explicit trade-offs between those connections, and importantly, it's adaptive and embraces change. Using this framework, stakeholders and resource managers can develop best management practices that can exploit the highest sustainable use of our marine resources while inducing the least harm in the social ecological system, finding solutions that are achievable, affordable, and acceptable to stakeholders. Understanding habitat use within estuaries has been long studied. However, previous studies have often been disconnected from each other using a variety of sampling analysis methods and data analysis methods that makes results hard to interpret between regional study sites. This research was conducted as part of a consortia effort between California, Oregon, and Washington to create a standard sampling methodology in hopes that data collected will be more generalizable across those regions and we'll have a larger baseline data set. This research takes advantage of recent advances in video and battery technology that allow for more complete look at communities over the diurnal period, meaning both day and night, also known as a diurnal and nocturnal period. And that brings us to the focus of this talk after a rather long-winded intro, which is understanding the role of shellfish aquaculture as functional habitat in the intertidal estuary. My work was focused on the Pacific oyster aquaculture in Tillamook Bay, Oregon, and builds on previous research that characterizes fish and invertebrate communities that occupy shellfish and eelgrass habitat. I was interested in how community structure changes over the diel period in and around aquaculture and how it's influenced by tidal cycles. Specifically, I looked at species composition, abundance, and diversity between habitats using underwater video and beach scenes. These 3 photos are some of our sample sites in Tillamook Bay. So again, we have some off-bottom aquaculture up to the top right using long lines. We have some on-bottom aquaculture, and then we have on-bottom aquaculture mixed with eelgrass. So one of the biggest hurdles of doing remote video survey work is being able to collect continuous footage over multiple days. Some of the previous research in this field has been done with GoPro style cameras that have largely limited observations due to a couple hours due to the battery life. These surveys were labor intensive, requiring frequent battery changes between tidal cycles, and we're only able to capture part of the tidal cycle because the battery would die before the end of low tide. And filming at night also proved to be a challenge due to the logistics of getting out to the field at night and due to the power consumption of video lights. So we worked with the Sexton Corp in Salem, Oregon to design a camera system capable of extended deployments that were able to capture the entire diel cycle day and night over the length of the study without having to go into the field every 6 hours and changing the battery. We did walk out to the field every day and kind of clean the lenses and make sure there weren't any algae obstructing the camera lens. So with minor maintenance, we were able to collect a lot more data with a lot less effort than had been done in the past. This work was performed by placing 7 cameras in differing habitats of eelgrass densities and oyster culture methods. These were dense eelgrass, sparse eelgrass, and sites without eelgrass, and sites with on-bottom, off-bottom, or no aquaculture. Sites were largely chosen by their accessibility from both boat and shore, and were separated from each other by at least 30 meters to avoid any edge conflicts of other habitats. So cameras recorded in 2-minute on, 10-minute off intervals over the course of 4 days and 6 tidal cycles. A Secchi disc was placed 1 meter in front of the camera lens to provide a visual frame of reference for water clarity and to mark the sampling frame. A downward facing camera was used in 2 eelgrass habitats to assess the differences in camera angle on the observed community composition. Then in addition to the video effort, we used a paired scening effort, which was conducted the following week. Previous studies have reported a sampling bias between survey methodology in the communities observed, so it's important to use multiple methods to fully understand the community we're observing. The fish were captured in the scenes, which we did 3 scenes at each site where we had a camera. And fish were identified and then released, except for a small number of fish that were provided to Jason Toft's lab at University of Washington for gut content analysis for a separate study. The figure on the left shows our sample sites in Tillamook Bay and screenshots from each of the sample locations. So out toward the main channel in this area, we had a lot of eelgrass habitat, dense eelgrass habitat. And then closer in, we had some sparse eelgrass habitats mixed in with some just muddy bottom, which caused some problems with visibility that I'll discuss about later. And then, yeah, the photos to the right are our camera setup in the field and us basically conducting the scening effort in some off-bottom aquaculture habitat, which was pretty difficult, trying to weave a net between these kind of PVC stakes that were placed in the ground. The video was reviewed by myself, and all Nectin observed were identified as species. I developed this water clarity index to provide a qualitative metric that could be used to exclude samples from analysis due to poor visibility. We had a lot of 1s and 2s, but occasionally we had some 3s and 4s, especially in sites with eelgrass, which filters suspended particulates from the water column. The total Nectin counts from the video were converted to an observation per unit effort, which is similar to a catch per unit effort, and that we were observing animals rather than catching them. Videos that received a 0 visibility score indicated that there was less than 1 meter of visibility, and these were not included in the analysis. Other videos that were excluded included when the lens became obstructed by eelgrass or ulva, which is another type of marine algae. Over 600 videos were removed from analysis due to poor water quality, and 96 were removed for camera obstruction. The scening data was analyzed using the total counts per scene, then averaged for 10 meters squared as an actual radius of the, or the diameter of the scenes was about 12 meters. So just kind of standardize it to 10 meters to kind of be a little more clean numbers wise. So here's an example of some of the video we captured. You'll see a shiner perch, staghorn sculpin, and an invasive green crab, which are becoming a larger issue here in the Pacific Northwest. The video survey produced 1,600 2-minute video samples totaling 57 hours of footage. From these, 2,400 individuals were observed from 21 taxa. The scening effort captured 855 individuals from 20 taxa. And in total, individuals from 27 taxa were represented, accounting for about half of the species known to occupy Tillamook Bay from other historical surveys, which have more extensively covered the region. So from these data, a Bray-Curtis similarity matrix was created using square root transformed observations per unit effort by species and habitat. The matrix was used to perform a NMDS, or non-metric multidimensional scaling analysis, which is a way to visualize data in multidimensional space. The key takeaway here is that points that are closer together are more similar. Each point represents the Nectin community abundance for each habitat and replicate, which here were the daily samples separated by the diurnal and nocturnal period. 2 dimensions were chosen for this analysis because they met the stress threshold of 0.2 or below, and adding further dimensions, meaning if we turn this into a 3-dimensional graph, it would have kind of complicated the interpretation of the results when our stress was already at a low enough threshold where we can understand this effectively. The graph on the right shows a clustering of nocturnal points and greater variation in the diurnal points. Visually, this indicates there's a strong difference between the community composition between the diurnal and the nocturnal periods, and fewer differences were observed between communities, between the nighttime communities, than we saw during the day. This was followed by a permanova analysis, or permutational analysis of variance, which was ran on 3 fixed factors of diel period with 2 levels, day and night, oyster culture type with 3 levels, on bottom, off bottom, and no culture, and eelgrass density, which was sparse, dense, and without eelgrass. And those densities were kind of haphazardly selected. We didn't actually count shoots and measure the density, but we kind of got a general feel, you know, this grass is thick, this grass is thin. So that was a qualification for that. And then we used 1 random factor of the sampling date, which was 4 levels, which were the day of each survey. So the analysis determined that the differences between the diel cycle and the influence of eelgrass was just statistically significant. So the Permanova was then followed, and the NMDS was followed by a principal component analysis, which describes variation of the data along the X and Y axes. This was overlaid with a Pearson correlation of the 7 most abundant species, which provides a line with the magnitude and direction indicating each species' importance and its contribution to the multivariate community structure, which consists of species combinations with the defined factors of eelgrass density, oyster culture type, diel period, and sample date. So you can see that smelt drive a lot of variation in the nocturnal community up here, while shiner perch kind of drive equal variance between the diurnal and the nocturnal community, because the shiner perch were equally abundant day and night, where the smelt in the video were pretty much entirely nocturnal. And so by kind of getting a feel for those two, you can look at the other species and get a sense of where they're driving variance within this community. No species were excluded from analysis during for my analysis because previous studies have indicated that, you know, removing even highly abundant or low abundant species can affect the overall composition analysis of the community. And I thought it was important to understand the minute details of animals that weren't usually included in analysis, such as polychaete worms, which are important prey items for some of these fish, and eelgrass isopods. Because we see such strong differences in diurnal and nocturnal nekton community composition, it makes sense to look at daytime and nighttime communities separately. If you look at the key, you can see that sites with eelgrass are green, sites without eelgrass are red, and sites with oysters are solid. So the Permanova results, using the same factors as previous, indicate the diurnal communities differ both by eelgrass density and oyster culture type. Now, looking to the graph to the right, we see that shiner perch, saddleback gunnel, and eelgrass isopods are driving variance, community variance, towards the eelgrass. My pointer is not very bright, but towards the eelgrass habitats. We also see that solid green habitats, those with oysters and eelgrass, have communities that are generally more similar to each other than those sites of similar eelgrass density without aquaculture. So we can see in this area here, we have sparse and dense eelgrass with aquaculture, and the sparse eelgrass with aquaculture is clustering more closely to the dense eelgrass sites than the sparse eelgrass without aquaculture. Now, this is telling us that adding on-bottom aquaculture with eelgrass is affecting the community composition. So, let's see. Yeah, I think that was the main point for that one. So when we look at the nocturnal trends, we kind of see a more messy picture. The plot shows a variation in the community composition that's driven by individual species is more spread out between habitats. And a Permanova revealed that eelgrass density and oyster aquaculture type were not significant drivers of multivariate community composition at night. So in the previous graph where we had good separation of all these habitats, they were kind of, you know, choosing their own corners to hang out in. We have a lot more mingling happening here, indicating that habitat use is much more indiscriminate at night. The seeding effort reveals a different community composition than the video effort, but similar trends of habitat use, with shiner perch and saddleback gunnel still driving variance in eelgrass habitat, and staghorn sculpin driving variance in habitats without aquaculture. And again, we see more similar communities using eelgrass and off-bottom culture habitats than we do with bare habitats. Here, a permanova also determined that eelgrass density and oyster culture type were both significant drivers of community composition as they were in the video data. The similarities between the diurnal video data and the beach scene data sets are somewhat surprising because each method captured very different relative abundances of each species. For example, Shiner perch accounted for 43% of all video observations, but only 12% of scene captured counts. Yet Shiner perch are still one of the largest drivers of variance in eelgrass habitat for both data sets. Also, smelt were almost entirely absent from diurnal video, but they represented 8% of diurnal scene captures. So that's just turned out to be very interesting differences between the effectiveness of each sampling method on capturing the community. So despite the differences in species-specific abundance and species composition between the sampling methodologies, we see similar trends in multivariate community composition using bootstrapped averages and multidimensional scaling of the 95% confidence regions. Now, those are all lots of big words. But so bootstrapped averaging is a technique that uses random sampling and replacement to better estimate variability in a data set, so that 95% of the population observed falls within the shaded area. Looking at this top eelgrass row, we can see that nectin communities are unique across eelgrass density, both by sample method and the diurnal period between day and night, because we have very little overlap, if any, and we have good separation with kind of higher variance in sites without eelgrass than we do in sites with eelgrass. Oyster culture type shows community differences between on-bottom and no aquaculture sites, with off-bottom aquaculture in the orange here, showing greater variance that overlaps between the two. At night, we see a complete community overlap of these habitats, indicating they're being used more regardless of eelgrass cover or aquaculture type. More broadly, we can look at just the presence or absence of aquaculture, which again shows striking similarity between the diurnal sampling methods of video and scene. And at night, we see some overlap of those communities, but it's less extreme than if we were just looking at aquaculture type. So the day-night differences here support other findings in the literature that report species to be habitat specialists by the day and habitat generalists by night, indicating the habitat offered by aquaculture has maybe greater use at night compared to day. This is an important consideration when evaluating shellfish aquaculture as habitat, especially because much of the previous work has largely focused on the diurnal period and hasn't spent a lot of time capturing the nocturnal period. And one interesting reason that fish may be able to use aquaculture habitat at night, or just more habitats at night in general, is because during the daytime, they often use structure to essentially hide from predation. And at night, they can use the cover of night and basically travel with less risk of being, consumed by another fish. So when we look at species-specific habitat associations, only a few fish show significant differences between habitat use. During diurnal hours, both shiner perch and saddleback gunnel were eelgrass associated, and staghorn sculpin were associated at sites without aquaculture present. As discussed in the previous slide, habitat use was more general at night, and no differences were observed between habitat associations of individual species during nocturnal hours. However, greater abundance of smelt and polychaete worms was observed at night across habitats. The graphs to the right show the results of a Wilcoxon test followed by a post hoc analysis using Dunn's method for joint ranking, which describes groups not connected by the same letter being significantly different. So this, so get my pointer working. So this is graph of a shiner perch, if you can read that, and then from the video data. And so shiner perch have greatest density in, or abundance in sparse eelgrass habitat. And they kind of have the same abundance in dense habitat, but they're also not dissimilar from eelgrass or sites without eelgrass. So yeah, no eelgrass and dense eelgrass are similar, where sparse eelgrass and dense eelgrass have equally high abundances. And so then we also see the staghorn sculpin are more abundant in sites without aquaculture than in eelgrass. So some of these differences could have been perhaps lower counts in dense eelgrass because they were harder to count, or perhaps shiner perch preferred to swim in less dense eelgrass because they're getting tangled up less. So there's some environmental characteristics to kind of understand why we get these numbers. An interesting finding was that while the total abundance of nectin did not differ over the tidal cycle, several species exhibit combined tidal and habitat effects. Shiner perch, for example, had greatest abundance in sparse eelgrass habitats, but only during the ebb tide, if you're looking at ebb and flood separately. This may account for some discrepancies in other studies that report shiner perch to have weak or no association with eelgrass. If those studies were not able to sample over the entire ebb tide due to battery constraints, they could have missed a window that shiner perch most use that habitat. Smelt and polychaete worms appeared on nocturnal flood tides, with smelt retreating gradually on the ebb tide, and polychaete worms returning to the burrows exactly at slack tide. This tidally influenced behavior on habitat use may help some organisms, such as polychaete worms, remain close to their burrows, or in the case of smelt, ensure that they don't become stranded at low tide. Conversely, we found that some species, such as English sole, were more abundant during ebb tides, perhaps because they're at less risk of dying if they became stranded during low tide. I guess yeah, so these graphs here are kind of the same as the previous, where the connecting letters show the similar groups. So shiner perch have greatest abundance in these two habitats, while these two habitats of sparse eelgrass, while we're looking at diurnal ebb tide only. So, and also included in there is the off-bottom habitat, indicating that there's potentially a little bit more similarity between eelgrass and off-bottom habitats. So the Shannon-Wiener Diversity Index was used to assess cup of water, sorry. The Shannon-Wiener Diversity Index was used to assess species diversity because it accounts for both species richness and evenness. We found that sites with on-bottom aquaculture that were co-located with eelgrass had the greatest species diversity and species richness. The graph above shows habitat level differences in species abundance using an ANOVA and post hoc Tukey-Kramer analysis. And the x-axis is formatted in such a way that the eelgrass density is listed first, then the aquaculture type. For example, dense dot bottom indicates dense eelgrass with on-bottom aquaculture. The key takeaway here is that sites with eelgrass and aquaculture have the greatest diversity. Also, sites with off-bottom aquaculture resemble sites with eelgrass along with bare bottom habitat. Unfortunately, no observations were made during diurnal hours in unvegetated on-bottom aquaculture habitat due to poor visibility, despite having excellent visibility, a quarter mile away at our other sites. If we look at the table below, you'll see that species richness is greatest where aquaculture is co-located with eelgrass. This is especially important and evident when combining species observations from counts of using both sampling methods, indicating that effective surveys should employ a multi-prong approach to sampling. So we can see again here the highest species or Shannon Wiener diversity is in sites with eelgrass and aquaculture or in dense eelgrass. And this bottom row here is a combined diel, video, and scene data, which basically counts up every species that was caught in that habitat using both methods. And again, we see the highest diversity of species in the dense eelgrass with on-bottom aquaculture. So in conclusion, nectin community structure varies over the diel period with greater variance observed when between habitats during the diurnal period. Most species are habitat generalists, with some species-specific habitat associations occurring during the diurnal period, but none during the nocturnal period. The ebb and flood tidal cycles are significant predictors of community structure and species-specific abundance. However, tidal cycle does not appear to greatly influence specific habitat use. And the presence of shellfish aquaculture generally increases species richness and diversity, with the greatest impact observed when shellfish aquaculture is co-located with eelgrass. Future research should take advantage of advancements in new technology to collect higher resolution data using a multi-pronged survey approach that uses both fisheries independent sampling techniques such as underwater video and fisheries dependent techniques such as scene, netting, hook and line, or traps. Because the results here are not inherently generalizable across regions, researchers should also focus on the impacts of aquaculture, perhaps using a Backy study or before-after control impact design to understand the mechanisms that drive community variance in intertidal habitat. This can be done by using existing baseline data and working with farmers to monitor changes in plot management to better understand the impacts of aquaculture and if certain changes may exert predictable responses from the nectin communities. Ideally, I'd like to set up a similar system to the one we designed, but capable of remotely transmitting photos in real time, so that sites could be monitored daily with limited need for camera maintenance. This would provide a fine-scale data set that could provide more complete picture of how aquaculture influences habitat use, accounting for seasonality and diel trends while capturing movements of the full tidal cycle. Let's see, the camera system designed for this study is a valuable tool that can help further research in this field by reducing some of the sampling limitations previously experienced. Our findings highlight the importance of eelgrass meadows to estuarine ecology, but also document synergistic effects observed on species richness and diversity when shellfish aquaculture is co-located with eelgrass. These interactions should be considered by resource managers and policymakers when considering how to advance sustainable shellfish aquaculture development. And with that, I'd like to thank my advisor, Dr. Brett Dumbold, and members of my committee, Steve Runrill, Scott Happel, and our now retired program director, Flaxen Conway, and to those who have helped me in the field with my analysis and field work, including Nate Lewis and Brooke McIntyre and Annie Merrill. We also worked closely with members of the West Coast Aquaculture Collaborative, including Kate Houle, Fiona Boardman, and Jennifer Rusink, who helped to establish data processing protocols for this study. Special thanks to my MRM cohort and alumni, especially Daniel Sund, who provided me with valuable insight throughout my graduate career. Finally, I must thank our industry partners, Pacific Seafood, who we worked with closely to facilitate field work in Tillamook Bay. And finally, I must thank my friends and family for supporting me over the last few years, especially my wife, Tori, who has worked hard as a nurse during this pandemic as I was buried in coursework. And thank you all for your support for coming here and those of you online. And with that, I'd like to open the floor to any questions.
All right, for folks in the room, if you have questions, just raise your hand and we'll bring you a mic. For folks online, if you want to type in your questions into the chat box, Tori's going to monitor those questions and read them out to us.
Questions? Chris.
Hi there. Very nice talk and very much enjoyed it. Chris Langdon here. I just had a question about how you can explain the difference between the results from the seine versus the camera. Why are there these differences you see?
Yeah, so the camera basically captures, due to the camera angle, we captured a lot of the kind of epibenthic community and like the demersal fish that may have been less prone to be captured by the fishing nets. So fish that could swim faster, like the shiner perch, they were less prone to be captured by the net. And then species such as the staghorn sculpin, they're kind of right on the bottom, the nets could have dragged over them and just not captured them. And then one thing I have been trying to figure out is, why haven't we seen as many smelt in the video as we did in the scene? And that one, I'm not sure, because we did not really see, I think I saw a total of 17 smelt during the daytime videos, and the scening effort caught about 80 smelt. So it could have just been coincidence for some things and just the effectiveness on camera angle, and basically the ability of the scene to capture things, and especially for cryptic fish like English sole were basically an inch long and translucent when we caught them in the scene, and you'd never be able to see those on video. And the English sole that we did see on video were larger individuals of about 4 to 6 inches. But yeah, thank you.
You got some online?
So we have an online question from John Chapman. Says, much of the day-night variation seems likely due to greater movements at night. It seems logical that abundance increases at night among the most mobile species. We're using the habitats instead of passing through. Does your data or parsimony show this?
Yeah, so the data shows a movement of smelt, specifically coming in with the flood tide and kind of leaving with the ebb tide. But outside of that, a lot of the other species didn't really exhibit specific kind of tidal movements, or were kind of equally abundant regardless if they were on the ebb or flood tide. And how I did that analysis was I basically, I didn't really divide it between slack tide and ebb and flood, which a lot of other studies have specifically just looked at slack tide when there's no water movement. But I did find in general that some organisms basically kind of detected, like, the water's not moving now, we're gonna kind of hang out and use this area more. But they weren't necessarily transiting as fast during the slack tide. But yeah. Does that answer the question?
Austin, I want to say just again, thanks for, really an excellent presentation, really good graphics and such. I enjoyed learning from you here. My question is, your results are showing habitat separation primarily during the day and less at night. And I want to ask you, so the interpretation is that then they're free from or freer from predation. So what predators then would be driving that? And the flip side of that question is, to what extent are they staghorns, for example? We just saw the staghorns out preying upon the worms.
Mhm.
To what extent could those patterns that you've shown here reflect predation by the communities themselves foraging upon each other at night?
Yeah, so there's a lot of larger fish that could be driving predation. Some of the perch, there's lots of sharks in the estuary. So we have higher level predators that basically are kind of having might have a hard time finding these animals, or they're hiding in the eelgrass or wrapped up within the aquaculture structure. And so with animals feeling more free to move, it could also provide opportunity for animals like the staghorn sculpin to kind of take advantage of that and basically kind of an ambush predator. So when they're close enough, they can basically come upon them and attack them. Yeah, Kelly.
Good job. That was great. Did you cover this? Maybe I missed it. At the beginning, you said you had a forward-looking camera and a downward-looking camera. Did you see a big difference in the diversity and abundance in those two differences?
Yeah, so I didn't go into that much with this presentation because there's a lot to cover. But so yeah, the forward-facing cameras caught a lot of the kind of fish that were living kind of above the eelgrass even. By the downward-facing camera, we saw like 1,000% or so increase in the number of crab we saw and flatfish, and a lot more staghorn sculpin as well. So the downward-facing camera would be a much better camera angle to use if you specifically wanted to look at English sole and were less interested in shiner perch, for instance. Oh.
So this is from Flaxen Conway. She says, you stated at the end that this work should be interesting and helpful to policymakers. Can you provide me with an example of a policymaker, fed or state, that you'd visit with about this work and a possible policy direction that this work could inform?
Okay. Let's see. So I've talked with Steve a little bit because he's on my committee. And so the findings here basically show that when aquaculture is co-located with the eelgrass, we do see higher abundances or higher species richness and diversity, which kind of indicates that we may have a healthier ecosystem when we have that diversity. Now, there are conflicts with the oyster aquaculture industry as far as harvesting methods go. So if harvesting is shown to be potentially detrimental to the eelgrass habitat, either by mechanically harvesting or, basically reducing or just causing negative impacts through the harvesting, you can't you can't just say, let's only grow oysters with eelgrass, because there's other effects to be considered as well. But from a management standpoint, it's something that should be considered, that shellfish aquaculture does bring some value, and it's not all detrimental to the coastal estuarine ecosystems.
Hey, Austin. Great presentation. I have a twofold question for you. First, were the downward facing cameras included in the analysis?
The downward facing cameras were not included in the NMDS or Permanova or any of that main analysis I just went over. We basically kind of threw those out there as kind of a pilot study to determine, as we move forward with this project and collect more data in the field, which camera angle is gonna basically get us the best data for the species that the project's interested. Brett's specifically interested in English sole and Dungeness crab. So in future studies, I think the primary data collection will come from downward facing cameras, or maybe somewhere in between the two that can better capture the species of interest.
And then the second part of that question, since they weren't included in the analyses, and rightfully so, did you do any sort of analysis on those? And you may not have had a large enough sample size, but did you see similar differences in the species captured, for instance, English sole and Dungeness crab, scalar to those that were in the other angle, or were they different?
So there was a much greater abundance of Dungeness crab. There was about, I think, 6 or 8 times more Dungeness crab seen on the downward facing, if I'm understanding your question correctly.
Yeah, I got that the differences, that there were many more seen on those downward facing ones, but did you notice any differences? Let me reiterate, any habitat differences, any of the differences among variables for those species?
Okay, so
unlike
we
what
only
we see.
used, because we only used 2 habitats, we only looked at sparse eelgrass with and without aquaculture. I didn't actually run the full analysis because we were mostly just interested in the raw number of what's going to be better for future studies.
Great, thanks.
How about day night? Was there a day night difference for those 2 species, or did you look at
I
that?
actually didn't look at day night differences between the forward and downward. Maybe I should have.
Great presentation. Also kind of going back to your analysis and things like that, you were saying there's a lot of videos that got thrown out due to poor visibility. Did you look at, I guess, either, tidal patterns, level, and, if it was a very extreme tide or, low tide or seasonality? Did you do any of that kind of analysis to help figure out what were your best visibility days for, if you were going to go out and repeat the study, you would focus on those days to hopefully get more video that's, accessible for your data?
Yeah, so the visibility seemed to be largely kind of like very locally dependent. So the sites that were most out in the channel, I can maybe go back to my sampling area or figure. Okay, so sites that were closer to the main channel, like E, B, and F, those had excellent visibility of 2 meters plus, while at the same time, on the same conditions, the sites inland, C and B, which were either just bare sediment or on bottom, were completely kind of fogged out. So I think in future studies, it would be important to, as much as possible, try to find sample sites that are kind of maybe closer, maybe to the main channel could be one of the issues, but having just the eelgrass naturally filtering the suspended sediment likely really increase the visibility. So in general, video sampling may not be the best method to use for those types of habitats. And that's kind of where we work in with other fisheries dependent sampling methods, where we can kind of look at the data together and kind of use that as a crutch for the video.
I had a quick question about the cameras at night. It sounds like you were using a light, an LED light. Did
Mhm.
you address the attraction for critters to that light in your sampling in comparison to day?
So as much as possible, so part of the NMDS requirements so that you're not double counting species. And so if it was obvious, sometimes a smelt would kind of be doing a loop and it'd come into frame, and then about 4 seconds later it would come back into frame. And in that instance, we wouldn't count that fish twice. And so in large, we did our best to not count fish. There were some instances of like staghorn sculpin, which were actually kind of observed using the lights to fish once or twice. So a lot of zooplankton's positively phototactic. And so we got some shrimp right in front of the camera, and the staghorn sculpin saw it and just came up and attacked it. And if there were, in that instance, each time that staghorn sculpin came back, I had only counted it once. And then because the lights are off for 8 minutes, I feel like there's enough time for fish to transit, and the visibility is so low that we're not attracting fish. Like if we were in Hawaii with 180 feet of visibility, we could be attracting fish from a greater range, but due to the low visibility, I feel it's kind of a reduced kind of impact of that.
Great presentation, especially for someone that's not in the science community. What was the most challenging part of your research, and what was the most fun?
That's a hard question. So I think in general, just like with the COVID complications, I think were the hardest part of this graduate experience was not having your traditional community and networking opportunities. And yeah, and then but to some point, that did work to my advantage, because I'm going to email a professor I don't know to ask a random question. There's no difference between me emailing somebody in New Zealand and asking them a question. So I was actually chatting with people all over the world, and I think they were more receptive to helping me because we're kind of in this new digital landscape. So I did get some communication out of it that way. And my favorite part of this project was working with Sexton Corp to design these cameras and getting them working and in the field. It was pretty exciting, and I was like very happy to have Brett's support in purchasing those cameras, and very enthusiastically supported me in that, and it was a lot of fun.
If you could redesign the cameras or add a feature to them for future studies, what would you do?
Yeah, so I think the main thing would be, it'd be awesome to have kind of remote cellular capability, so we could have kind of a live feed, and then we could potentially place one camera out in the field and have a live kind of video footage of water clarity. And then when we know the water is clear, then we can deploy the rest of the cameras. So having something like that would be really awesome. But then also so these run on a kind of simple Arduino computer program that's ran on a programming language, Python, on the back end. But having ability to create multiple start times would be a good programming feature to add. Currently, they're set up for basically one start time, and they're all synchronized, but it's continuous recording. So I had a lot of videos to kind of manually delete after each thing. And then that would also extend the battery life. So right now, these things ran about 120 plus hours with continual coverage and lights running 12 hours a day. If we were able to limit start-stop times a little bit more, we could probably stretch that out to a week or more. And if we wanted to do something like photo time lapse rather than video, we could deploy these cameras for like a year and have a greater kind of high resolution data set. We just have to figure out how to keep the lenses clean.
Okay. Are we done online too?
Great presentation, Austin. I really enjoying this impact these cameras have on this study and the issues you're having to deal with. You mentioned the green crab is invasive.
Mhm.
Did you see any more of them or any other invasive species?
Yeah, we saw a lot of green crab, especially during the seeding effort, which, yeah, those have to be, if you catch a green crab in Oregon, you're supposed to euthanize it. So it's a little bit of that, but the green crabs are becoming more and more prevalent. And they're now here in Yaquina Bay, especially further upriver around the oyster aquaculture sites. And there's a lot more than we anticipated seeing, I think. We saw about 30 green crab on the downward facing camera over 3 days. And there's a lot of effort, especially going on in Washington right now to fight their expansion. They have a lot of funding to do that up there. I'm not sure where ODFW is on that position right now, but I think it's becoming more of a concern. Yeah.
I guess one more.
Kind of piggybacking the same question, is there any sort of effort to have people catch green crab? Is it edible? Is the meat good? Or are they small enough that it's not worth it?
Yeah, I don't think there's much of an effort. They're not highly dense or abundant in the sense where I think WDFW put out 2,000, or I don't know, they had like a couple hundred traps and they caught 2,000 green crab over the course of a couple of years, I believe. So they're not highly dense where you can throw out a pot and get them like Dungeness crab. And they're kind of smaller, like the red rock crab fishery.
That's not the impression I got recently in Willapa anyway, but that you theoretically could. I just don't know whether they're harvesting them for, they're not, there's no incentive to harvest them to eat.
Yeah.
That's looking at me. Am I on trial here?
Uh-huh.
No, so we're ODFW. We have an active monitoring program going on that's been going on for decades here in Oregon to keep track of the populations of green crab. And as you all probably are aware, their numbers have really gone up over the last several years. So unlike Washington, we have not started an effort to eradicate them or try to trap them out. At this point, the feeling is they're here. They arrived in Oregon and rapidly expanded up, established populations over a period of 2 years back in the 90s. They've been here for a long time. The second issue, though, is they're increasing in abundance now. And so we are actively engaged with the Oregon Invasive Species Council, putting together an ecological risk assessment to try to figure out just what their ecological damage may be. When that's completed, that'll also have a socio-cultural assessment as well. And then we'll move forward with our decision on how to deal with them here. Thanks.
All right, that's sort of an offshoot from your stuff.
Yeah, a
Looks
little
like
bit.
we're done with the questions for the most part here. So thank everyone for coming. Since I know Flaxen's online, thanks Flaxen for
Yeah,
bringing
thanks
us.
to everybody online.
But thank you. Thank you all. And to the committee members, we will take a break here for a little bit, 10 minutes, and we are to meet with Austin on the 3rd floor. I don't know the room number, but on the third floor.
It's the little conference room. So if you take the elevator up, it'll be off to your left.
All right, bye, guys. Thank you. Okay.